Hi everyone and welcome to a brand new video. So today we're going to be tackling this problem which says that given the root of a binary tree, return the same tree where every subtree does not containing a 1 has been removed. So basically you have a tree and you need to remove all the sub-branches that don't have a 1. So for example, in this example I can draw it out. We have 1 which is right node is 0, whose left node is 0, and whose right node is a 1. So over here you can see that this tree subtree doesn't have a 1, which is bad. So we're going to remove it. But the rest of it does, because this subtree has a 1 here, even though this isn't a 1 itself, it has a 1 in its bottom. So this is what we would return, as you can see here. So how would we tackle this problem? Well, you actually take 3 methods. So the first method is the normal method that it's the normal one with all the functions in it. Then the second one we are looking at is a contains method, contains 1. And this will see whether the subtree contains 1 in it. And then we have recursive, which will remove all of the subtrees that don't have 1. So I'm just going to create them. So private recursive doesn't need to return anything. So I'm just going to call it recursive, but it takes in a tree node. And then we also have private static boolean contains 1, and this does return a boolean to see whether or not it contains it. So first, let's start with contains 1. All you need to do is say that if root is equal to null, we want to return false. If root.val is equal to 1, we want to return true, and else we want to return contains 1 of root.left or contains 1 of root.right. And that's really simple. This just sees whether the subtree has a 1 in it. So now we need to use this inside recursive. And in order to do this, I'm going to say that if root.left is not equal to null, then we see if it doesn't contain, if contains 1, root.left is false, then root.left is going to be equal to null, and else we're going to call recursive a root.left because there might be a 1 in it. As you can see here, yeah, there's a 1 here, but if you get to another node below, there might be a subtree that doesn't have it. It's kind of like taking credit for something you don't have. We want to remove all of those. And then we're going to do the exact same thing with root.right. So I'll just copy paste that and change these all to right. Perfect. And the last thing we need to do is finish the original function. And in order to do that, all we need to do is store the original node so that we can call recursive on root, and then we can return original. Because root will probably be some at the bottom of one of the subtrees. So it's just better to store the original node because then you can return it. One minor thing we need to keep in consideration here is that this only deals with left and right. And that's because you need to make left null, right null. You can't make like the node null. So in order to account for maybe the first node itself, maybe that doesn't have a 1 in it. So by the time you're done with recursive, and if that's true, then you only have 1 node left. So that's why we need to say that if not contains one of original, then we can just return null, right? Because there will only be one node left. So this is our complete function, or our complete code. Looks like there's an error. Let's see what that is. Oh, so it looks like I accidentally added an extra comment there. So let me just remove that. And perfect, perfect. So now if we run our code, oops, let me put dot files here. You can see that we get the 101 that we're supposed to, and let me try root.right.left. Let's see whether that's removed. And then let's see what it prints out. As you can see, it throws an error because it is null. So therefore, we have successfully created the we've successfully solved this problem. So I hope this was helpful and see you in the next video. Bye.